December 16, 1944, at 0531 hours near Mancha on the German-Belgian frontier. Colonel Oscar Alfred Axelson from the U.S. 46th Artillery Group gazed into the dim light before dawn at the sealed ammunition containers, fully aware that his impending choice would defy directives from the top echelons of Allied leadership. Peering through his binoculars, he observed German troops gathering for what would prove to be Hitler's final frantic push in the Western Theater. Operation Watch on the Rhine. The 38th Cavalry Squadron, guarding the northern flank of the engagement later known as the Battle of the Bulge, faced imminent overrun. "Sir, the enemy has started their barrage," his operations officer announced. "The 38th urgently needs artillery assistance." Axelson glanced toward the piles of projectiles, labeled with the restricted label T-98 Posit, proximity-fused shells prohibited for terrestrial deployment since their invention. The innovation was guarded so tightly that few U.S. officers even recognized it. Inside these rounds were tiny radio devices designed to trigger at exactly 30 feet overhead, generating a deadly spray of shrapnel that rendered conventional trenches ineffective as shelter. "Load the VT shells," Axelson commanded, employing the alias for variable time to mislead foe spies. "We'll deploy our full arsenal." In just 47 minutes, Axelson's unsanctioned call would expose German infantry to a device that reshaped the closing stages of World War II. These Airburst munitions featured tech so advanced that Nazi experts had dismissed it as unfeasible. Every unit embodied a feat of production that exposed the vast disparity between U.S. industrial prowess and Axis misconceptions of their adversary. The calculus of destruction stood on the brink of overhaul. Each projectile would burst roughly 30 feet in the air, unleashing a cone of hypersonic metal shards moving at 3,000 feet per second, blanketing a 60-yard area with fatal impact. Neither the depth of excavations, nor the profundity of dugouts, nor the sturdiness of improvised overhead barriers feasible amid battle could shield against this descending storm of projectiles. The proximity fuse ranked as the third pivotal tech breakthrough of World War II, trailing only radar and the atomic bomb, as verified by U.S. military evaluations. However, in contrast to those inventions, its presence stayed hidden from Axis troops right up to the moment they perished under its barrage. The mechanism was deceptively straightforward in theory, staggeringly intricate in practice. A compact radio sender and detector, compact enough for the front of an artillery round, resilient enough to endure 20,000 G-forces during launch, advanced enough to sense proximity to terrain and ignite at the ideal elevation for peak destruction. Every fuse incorporated 4 vacuum tubes, not 5, contrary to occasional claims, composing a full radio setup squeezed into a volume tinier than a mug, fortified against stresses that would pulverize flesh. Research kicked off in 1940, devouring $1 billion in wartime currency, equivalent to about $15 billion today. By the end of 1943, U.S. plants churned out 40,000 proximity fuses each day, scaling up to 70,000 daily as the conflict wrapped up. The UK research team that first observed the device hailed it as the war's greatest engineering triumph. Output figures underscored U.S. manufacturing dominance. Precisely 22,734,181 proximity fuses produced from 1942 to 1945, with 21,685,157 dispatched to battle zones and 324 allocated for trials. Each fuse comprised roughly 130 parts, machined to 100,000th inch precision, put together in sterile environments by 110,000 laborers who seldom grasped the end product. The energy challenge was addressed via a clever air-powered dynamo that engaged post-firing. A petite fan, shielded during propulsion, would deploy into the airflow, producing power to energize the condensers fueling the radio system, which ran at 180 to 220 metomeridians. Thus, the fuse remained dormant until launched, secure for transport, undetectable, and resistant to interference until its closing moments aloft. The initial large-scale use of proximity-fused rounds on land objectives unfolded at 118 hours on December 16, 1944, exactly 47 minutes following the launch of the German assault. Colonel Axelson's 46th Artillery Unit unleashed the barrage sans formal approval, addressing the pressing battlefield emergency. General Eisenhower delayed official permission until December 19th, with all bans removed by December 21st. The results were swift and catastrophic. As German troops pressed forward in the murky pre-dawn, they scrambled into their dug positions at the onset of U.S. cannon fire. Routine tactics they had executed artillery shells had been unleashed repeatedly. Rather than striking the earth, however, these projectiles detonated high in the sky overhead. Shrapnel rained down in trajectories that made Foxholes entirely ineffective. The after-action analysis from the 99th Infantry Division captured the consequences vividly. VT-fused barrages targeted German staging zones near Krinkel, inflicting devastating losses on forward battalions just 12 minutes into the bombardment. German field medics found themselves completely overrun. Assaulting troops had no choice but to trample their fallen comrades just to press onward. By December 23rd, intelligence assessments put the toll at 2,000 German fatalities from proximity-fused munitions amid the clashes near Malmö, where gun crews delivered punishing fire against SS units. Certain assailants, gripped by panic, allegedly rushed headlong into the barrage, screaming, "Kamerad!" The mental toll outstripped the bodily harm. To grasp how proximity fuses made conventional defenses irrelevant, it's essential to examine the mechanics of aerial explosions. A typical high-explosive round bursting on impact buries 50% of its fragments in the soil, scatters 45% sideways in a flat arc, and propels just 5% skyward. Troops hunkered in well-dug foxholes enjoyed a 90% survival rate against standard shelling. The proximity fuse upended those odds dramatically. Exploding at 30 feet above ground, it directed 100% of the debris downward or laterally in an upside-down cone. The danger zone expanded from 25 yards for surface impacts to 60 yards for overhead bursts. Even more vital, the shards descended at 30 to 45-degree angles, ideally positioned to penetrate foxholes, ditches, and weapon slits. The deadly coverage surged from 60 square feet under regular fuses to 3,000 square feet, a 50 times greater reach that neutralized most field entrenchments. This went beyond mere enhancements in firepower. It revolutionized infantry targeting tactics for artillery. The projectiles stood as testaments to U.S. engineering excellence. Their tiny parts endured stresses that would demolish ordinary circuits. The quartet of vacuum tubes, a triode handling oscillation and detection, a pentode for boosting signals, a thyrotron serving as the firing switch, and sometimes a diode for converting current, were ruggedized designs utterly unlike consumer versions. The proximity fuse's creation exemplified top-tier collaboration between American science and industry. In August 1940, the British Tizard delegation revealed key wartime innovations to the U.S., encompassing preliminary radar tech and the basic idea for a proximity fuse. UK researchers had validated the principle, yet their manufacturing base couldn't scale it up. The National Defense Research Committee, established in June 1940, ranked the proximity fuse as its runner-up focus behind radar. Johns Hopkins Applied Physics Laboratory took charge of prototyping as U.S. factories geared for mass output. The hurdles were immense. The mechanism needed to endure 20,000 Gs of setback force, perform across temperatures from 50 to 120 degrees Celsius, rotate at speeds up to 30,000 RPM, and remain dependable after prolonged warehousing in environments from muggy Pacific atolls to icy European storage sites. Section T, the project's secret moniker, peaked with 3,000 researchers and technicians. Innovations included impact-resistant polymers, compact vacuum tubes built to resist shattering pressures, and fabrication methods precise to a 10,000th of an inch. Initial triumph came on January 29, 1942, as a fuse-equipped shell downed a remote-controlled plane above Chesapeake Bay. Come August 1942, the USS Cleveland loaded up with proximity-fused anti-air rounds. Outcomes were astounding. Splashes against Japanese planes skyrocketed. The USS Helena etched a milestone on January 5, 1943, by dropping a Japanese bomber near Guadalcanal with merely 4 such shells. Yet, secrecy concerns barred land use, fearing foes might salvage dud ordnance. That caution persisted until the Ardennes push endangered Allied lines, compelling leaders like Colonel Axelson to deploy them illicitly, a move later vindicated. Prior to terrestrial application, proximity fuses had already reshaped sea combat. At sea, capture risks vanished, enabling full-throttle deployment versus Japanese aviators. The figures spoke volumes. Proximity armed vessels averaged 310 shots per kill versus 1,162 for time-fused shells. In 1944, these rounds comprised 25% of expended ammo, but notched 51% of enemy planes downed. During the bat in the skirmish of the Philippine Sea during June 1944, proximity fuses played a key role in what history remembers as the Great Marianas Turkey Shoot. Japanese aviators suffered over 400 aircraft destroyed, refining a device that later wreaked havoc on German foot soldiers. Meanwhile, the British started deploying these fuses against V-1 buzz bombs. On June 12, 1944, mere days following D-Day, coastal anti-aircraft units in England boosted their success rate from 17% to 79% over the next 4 weeks. General Sir Frederick Pyle, who led anti-aircraft operations, hailed it as warfare's greatest scientific breakthrough ever. Such triumphs rendered the ban on terrestrial applications harder to enforce. On-the-ground leaders were aware of the device's potential and chafed at seeing their troops suffer avoidable losses. The dire situation in the Battle of the Bulge ultimately shattered this administrative deadlock. Interestingly, German spies had picked up hints about proximity fuses. Back in October 1944, Staff under Field Marshal Albert Kesselring observed sharp spikes in Luftwaffe casualties from Allied flak. They examined debris showing odd markings indicative of mid-air explosions. Kesselring's dispatch to the OKW, Oberkommando der Wehrmacht, warned, "Indications point to the Americans having altitude-sensitive rounds. Should these shift to field guns, the toll on troop formations could be disastrous. Urge prompt exploration of defenses." Berlin's reply, unearthed in seized documents, brushed off the alert. Experts deemed proximity blasts unfeasible amid combat stresses. Gains in U.S. air defense were chalked up to better radar guidance and denser barrages. Nothing further needed. This oversight exacted a heavy price from the Wehrmacht. In truth, German researchers had pursued proximity fuse prototypes from the 1930s onward, experimenting with 30 to 50 variants like sound-activated acoustic types, electric field sensors, and radio-linked mechanisms. Yet none made it to the front lines. A 1940 order from Hitler, halting any project unable to go live in 6 months, doomed their efforts. The twist was stark. Amid the Bulge offensive, Axis troops seized around 20,000 of these fuses, but failed to grasp their value. Their technicians dismissed the idea as impractical, citing the extreme G-forces from gun launches. They possessed the war's ultimate espionage windfall right there, oblivious to it. 5 U.S. firms handled the end-stage assembly of proximity fuses. Crosley Corporation delivered 5.2 million units. Sylvania churned out 5.7 million. RCA, operating 2 facilities, assembled 5.9 million altogether. Eastman Kodak contributed 2.4 million, and McQueen Norris added 2.9 million. Sylvania's Ipswich, Massachusetts site stood out as the top producer, responsible for 26% of all units. At Crosley's Cincinnati facility, 8,000 staff members cranked out as many as 16,500 fuses each day during maximum output. Their inspection process spotted flaws down to the 15,000th of an inch. The operation guzzled more power daily than some full German urban areas. Cooling systems held temps steady within 2 degrees to avoid heat-induced warping of parts. Roughly 28% of finished products got scrapped for not passing muster, a rate that would cripple German factories but pose no issue for U.S. strategists, given the sheer scale. They trashed more high-tech parts in a day than the Reich managed in a month. Sylvania led in parts fabrication, supplying 95% of the tiny vacuum tubes, over 100 million in all, via 10,000 employees at 15 specialized VT fuse sites. More than 100 U.S. businesses joined the effort, backed by over 2,000 vendors from raw material producers to fine tool workshops. Women formed the bulk of the labor force. At Sylvania's Ipswich operation, 9,000 out of 10,000 personnel were female, drawn largely from nearby towns. They toiled in sterile environments with purified airflow, peering through magnifiers to confirm alignments precise to 20,000th of an inch. Most handled a single repetitive duty, cycling it thousands of times per shift. Come Christmas Day, 1944, these fuses saw action all along the Ardennes line. American forces unleashed 200,000 rounds fitted with proximity triggers in the Bulge campaign. General Patton, once dubious about the innovation, turned enthusiastic upon seeing results firsthand. Between December 25 and 26, his Third Army tallied about 700 German deaths, verified on site at Eckton through proximity-armed barrages. In his well-known remark, "The funny fuse won the Battle of the Bulge for us." Coming from a general who long prized armored thrusts and rapid maneuvers above all else, this shift spoke volumes. The mental toll on Axis troops proved. Interrogations of prisoners provided the evidence. Detainees from the German ranks often spoke of their utter powerlessness, facing barrages that detonated above them. Standard military drills had long stressed hunkering down in low spots, dugouts, or ditches for protection. Yet these spots turned into fatal hazards once proximity fuses entered the equation. A detained Wehrmacht lieutenant confided to his questioners, "Those rounds burst right at the level of the treetops, every time the exact same altitude. We experimented with all sorts of tactics, deeper pits, reinforced lids, spreading out our forces. None of it made a difference." The reliable 30-foot burst altitude, enabled by accurate radio detection, fostered a sense of inevitability that proved even more frightening than erratic strikes. The clash in the Hurtgen forest, ongoing from September 1944, shifted dramatically following the approval for proximity fuse deployment on December 18th. What had been a thick woodland offering German troops hiding spots and natural roofing now amplified the fuse's impact. Canopy explosions were inherently lethal, though tough to trigger on purpose using timed munitions. With proximity fuses, detonations occurred reliably at the ideal elevation, regardless of whether the terrain was barren or wooded. The mix of metal shrapnel and flying timber shards unleashed a deadly barrage that overwhelmed any frontline defenses. In the initial 48 hours after permission was granted, the 4th Infantry Division's gunners unleashed 12,000 rounds equipped with these fuses. Their post-battle summary highlighted a sharp rise in adversary losses, alongside a marked drop in the enemy's ability to hold ground. Aid posts documented unfamiliar injury types, penetrating gashes from overhead, focused mainly on the upper bodies and skulls. This engagement served as a somber testing ground for gauging the fuse's consequences. Forward spotters observed that enemy fighters abandoned their dugouts, opting instead for enclosed shelters like pillboxes and structures. Such clustering made them easy prey for standard blast rounds, presenting a strategic bind without viable escapes. Launched on February 23, 1945, Operation Grenade marked the Allies' push toward the Rhine. The Ninth Army expended hundreds of thousands of proximity-fused projectiles during its opening week. Fortifications the Germans had meticulously built over months fell prey to overhead blasts. The Wehrmacht released frantic commands in a bid to neutralize the fuse's advantages. A directive dated February 10th insisted that every outfit dig foxholes at least 2.5 meters deep, topped with logs no thinner than 30 centimeters and buried under 50 centimeters of soil. An update on February 18th demanded that under fire, troops move solely via shielded ditches. Every outpost needed cement or metal roofing. Such demands were utterly unfeasible amid active fighting. The resources and hours needed for building them simply weren't available. By February 26th, an order boiled down to, "We must spread out as far as operational needs allow, limit any spot to just 2 soldiers." The seizure of the Ludendorff Bridge at Remagen on March 7, 1945, highlighted both the fuse's strengths and their constraints. When Lieutenant Karl Timmermann called for fire support using VT fuses to hinder the German withdrawal over the span, the battery leader denied it, pointing to intelligence that American forces were dangerously near. This recorded denial, preserved in U.S. Army records, underscored the necessity of precise handling to prevent losses among allies. Efforts by the Germans to craft their version of the proximity fuse exposed the vast chasm in manufacturing prowess between the sides. Rheinmetall restarted its work in 1944 and even launched hundreds of functional test units before the conflict concluded. Still, these were mere trials, not geared for scale. German technicians figured they required 15 fresh electronics plants, instruction for 50,000 expert laborers, and novel assembly methods absent from their homeland. To match U.S. output, they'd demand 500 tons of pure copper each month, 50 tons of silver for connections, 2 million exact vacuum tubes, and 100,000 trained personnel. Even assuming supplies were on hand, their facilities missed the fine machining equipment essential. U.S. plants relied on Swiss micrometers precise to 100,000th of an inch. The Germans' top tools, battered after 5 years of non-stop use, managed 1,000th precision at best. Standards for quality assurance alone outstripped what they could handle. The greater twist lay in the fact that German researchers grasped the principles flawlessly. In truth, they had initiated proximity fuse studies ahead of the Americans, yet mastering the concept differed profoundly from ramping up to mass output. The U.S. didn't merely invent better devices, it forged a full production network able to churn them out by the millions. Although these fuses revolutionized land combat across Europe, their initial design goal, countering aircraft, attained its greatest success in the Pacific theater. By 1945, shells equipped with proximity fuses obliterated Japanese planes with remarkable success. The kamikaze danger, which could have turned a Japanese invasion into a disastrous endeavor, was mostly countered by these VT fuses. During the Okinawa operation, vessels employing proximity fuses downed 91 enemy aircraft out of every 100 assailants, a stark improvement over the previous 25 per 100 without them. Admiral Willis Lee remarked that proximity fuses preserved 100,000 American lives across the Pacific theater. Each Japanese aircraft felled by VT fuses meant one less threat to ram into U.S. vessels. This versatile technology proved ruinous to ground troops in Europe and pivotal against planes in the Pacific, embodying America's approach of manufacturing superior products on a massive scale and distributing them widely. Meanwhile, Germany grappled with even basic ammo production, confronting a foe that integrated advanced electronics into expendable projectiles. Studies by military experts on proximity fuse performance showed they were 3 to 10 times deadlier than standard shells against terrestrial objectives. When targeting V-1 buzz bombs, hit rates soared from 24% to 79%. In shipboard anti-air defenses, the shells needed per downed plane fell from more than 1,000 to around 300. The dramatic 50-fold expansion in the lethal zone of fragments revolutionized how artillery was used. Conventional barrages demanded dense volleys for broad coverage, but proximity fuses enabled scattered shots to deliver comparable results using far fewer rounds. Such shifts enhanced supply efficiency, minimized gun barrel degradation, and permitted batteries to aid additional frontline groups at once. General Patton noted that these fuses led his gunners back advancing troops more potently. Rather than drawn-out initial strikes, they unleashed brief, highly destructive barrages that enabled foot soldiers to push forward while foes were still reeling. This boosted pace of operations fueled the swift Allied breakthroughs of 1945. That said, casualty data demands scrutiny. Though rumors of exact tallies like 250,000 German fatalities from proximity fuses spread amid and post-war, no verified records back such figures. What records confirm is the fuses' amplification of artillery potency and their demoralizing effect on German troops. Awareness of this tech among Germans built slowly and partially. Interrogations of captives showed most frontline soldiers remained clueless about the source of their losses. They described overhead explosions like tree bursts or air mines, yet failed to comprehend the methodical innovation behind it. German intel on tech matters eventually acknowledged the complexity. Documents seized from March 1945 admitted the U.S. proximity fuse marked a 5-year leap in compact electronics. Copying it would demand a total overhaul of their electronics sector, novel materials not on hand, and at least 18 months of effort. their advice unfeasible given the circumstances. Germany's last military assessment, dated May 7, 1945, declared, U.S. guns using proximity bursts have caused more losses than every other armament together since December 1944. Defensive tactics have failed utterly. Advise halting combat right away to shield surviving units from obliteration by this advanced arsenal. The Proximity Fuse Initiative drew about 3% of America's physicists to one armament effort. This focused brainpower, paired with vast manufacturing might, yielded output numbers that baffled German analysts. Crossley Corporation's assembly lines churned out 500 units hourly. Employees handled precise tasks in mere seconds, repeating them countless times each shift. Plants ran nonstop 24/7. Even on Christmas 1944, production held steady as German troops fell to VT fuse barrages in the Ardennes. U.S. laborers sustained peak efficiency. The logistics network spanned the nation. Copper from Montana pits, silver from federal stocks, custom plastics from firms born just 3 years prior. The scale of industrial gearing up rivaled the fuse's ingenuity. In opposition, German shell output in 1945 depended on coerced labor, yielding only 60% usable items. Disruptions by unwilling workers cut viable production even more. By March 1945, just 30% of their artillery rounds worked as intended. U.S. VT fuses, for all their intricate circuits, hit 94% dependability. The tale of the proximity fuse goes beyond gadgets and figures. It reshaped the ground war reality for soldiers on either side. GIs felt empowered, assured their barrages could neutralize entrenched adversaries. Wehrmacht troops forfeited the long-held comfort of soil in foxholes. Veteran testimonies, accounts from participants on both sides, attest to this profound shift. U.S. artillery spotters reported directing barrages with greater assurance, confident that proximity fuses would strike foes even in fortified spots. German survivors remembered the dread of artillery shells approaching, realizing that hiding provided futile shelter. The effects on medicine were profound. Injuries from proximity fuses posed novel difficulties. The trajectory of shrapnel produced injury types unfamiliar to battlefield doctors. German field hospitals, overwhelmed as they were, struggled to respond to these emerging wound profiles. In comparison, U.S. medics benefited from penicillin and plasma transfusions, benefits unrelated to the fuses themselves, yet they amplified overall success. Beyond mere battlefield gains, the proximity fuse symbolized broader dominance in linking research, production, and armed forces deployment. As Germany chased miracle devices such as V-2 rockets, which devoured vast sums for scant combat impact, the U.S. churned out truly game-changing innovations and distributed them extensively. The V-2 initiative drained about $2 billion in comparable assets and claimed roughly 9,000 lives. By contrast, the fuse effort spent only half that amount and revolutionized both land and air defense artillery. Such a contrast highlights contrasting philosophies in wartime tech. Germany's fixation on bold breakthroughs against America's strategy of incremental enhancements produced in volume. The proximity fuse further affirmed U.S. collaborative processes. The partnership among Johns Hopkins researchers, factory producers, and frontline troops forged a pipeline that advanced from idea to widespread output in under 3 years. In Germany, disjointed labs and branch conflicts blocked comparable progress. Following the Nazi defeat, U.S. intelligence experts examined captured German fuse studies. They uncovered advanced concepts, but no viable route to assembly. German experts grasped the fundamentals, yet failed to conquer production hurdles. The Rheinmetall models found in 1945 functioned adequately in tests, but relied on standard vacuum tubes vulnerable to shell launches. German technicians experimented with reinforcement methods, but never matched the durability of U.S. versions. Moreover, even with success, Germany had no means for large-scale fabrication. Through Lend-Lease, Soviet troops got a modest supply of proximity fuses, though without blueprints. Their specialists took 7 years to dissect seized units before crafting homegrown ones in 1952. Quality, however, lagged behind wartime American standards. This diffusion of tech underscored the intricacies of fuse creation. Mere prototypes sufficed not. Effective output demanded robust factories, rigorous standards, and skilled processes honed over time. The tale of the proximity fuse imparts lasting insights into defense advancements. Primarily, refinements to proven tools can outmatch flashy inventions. Fuse enhanced conventional shells, yet they elevated gunnery to new heights. Next, scaling output rivals ingenuity and importance. Germany pioneered jets, guided missiles, and cutting-edge subs, but fielded too few to tip the scales. The U.S. fabricated millions of fuses, intricate electronics each, and used them like ordinary rounds. Thirdly, seamless ties across sectors shape combat strength. The fuse demanded synergy from labs, workshops, makers, and troops. America's teamwork ethos enabled this. Germany's silos stifled it. Lastly, classification yields edges, yet incurs drawbacks. Limiting fuse deployment until December 1944 safeguarded surprise, but allowed extra Allied losses that early use might have averted. Weighing concealment against field benefits endures as a dilemma in today's armaments. The proximity fuse provokes thorny ethical debates on mechanized conflict. It rendered death swifter, surer, calibrated with exact math. Troops in burrows faced shells bursting above at optimal altitudes, defenseless. This transcended classic fighting. It became mechanized carnage. Still, fuse accelerated war's end. Each Nazi unit shattered by such barrages weakened guards at death camps. The very tools that felled soldiers briskly also sped rescue for tyranny's prey. Admiral Lewis Strauss, who placed proximity fuses among the innovations on which triumph chiefly rested, grasped this moral sea. American service members grappled with the profound consequences of this innovation. They appreciated the tech that protected U.S. troops, yet were disturbed by its ruthless precision. Reports recount discovering Nazi strongholds where troops perished all at once from shrapnel of exploding shells in mid-air. This method of destruction stripped away personal involvement in the act of dying, making it coldly efficient. In essence, the proximity fuse embodied U.S. strengths that went beyond any one piece of equipment. It showcased the ability to churn out advanced devices on a massive scale, the expertise to tackle intricate challenges swiftly, and the skill to synchronize research, manufacturing, and deployment. During the German counteroffensive in December 1944, when foot soldiers encountered shells equipped with these fuses, they weren't just up against a novel tool, they were staring down the tangible power of America's industrial democracy. This framework allowed for inventing, refining, building, and fielding groundbreaking tech even as it waged war across the globe. That 30-foot span between the shell's burst and the ground hitting it symbolized the divide between U.S. prowess and Axis misconceptions. Encoded in that short gap, gauged by radio signals and controlled by tiny circuits, was the contrast between a free society's productivity and a regime's wasteful rigidity. The proximity fuse didn't just alter World War II, it ushered in the era of intelligent armaments. Today's pinpoint-guided projectiles owe their roots to the compact electronics first used in these fuses. What was a groundbreaking idea in 1944, embedding smarts into bullets, has become routine in armed forces worldwide. The assembly processes honed for these fuses shaped the electronics sector after the war. Standards for quality assurance, sterile environments, and meticulous putting together laid the groundwork for chip making. The female workers who put together proximity fuses back then blazed trails in methods that endure in modern device fabrication. The management insights were just as lasting. Blending university studies, factory output, and battlefield use set the pattern for arms creation in the Cold War. The effort around the proximity fuse proved that open societies could harness tech every bit as potently as dictatorships, maybe even better. This narrative draws from confirmed archives and solid proof. Output numbers stem from Bureau of Ordnance files. Design details pull from unclassified papers out of the Johns Hopkins Applied Physics Laboratory. Combat stories come from formal debriefs and war chronicles. Unsupported assertions got left out. There's no backing for exact death tolls often linked to these fuses. Efforts by Germans to disrupt them lack confirmation. Certain popular tales seem blended fictions instead of real occurrences. Even so, what's left after strict checking is impressive. The proximity fuse truly upended howitzers, shifting them from broad suppression to targeted strikes. Its creation and widespread rollout highlighted U.S. manufacturing dominance. Its battlefield use sped up the Allies' triumph. At that 30-foot height, free governance triumphed over tyranny, not solely via better principles, despite America's ethical edge, but via the everyday brilliance of large-scale making. The proximity fuse, with its shrunken circuits inside a howitzer round, captured all that the Nazi regime had wrongly judged about U.S. freedoms. Where the Germans viewed variety as a flaw, the Americans turned it into a force for rallying resources. Jewish researchers escaping Nazi oppression helped build the proximity fuse. Women barred from frontline duty built the munitions that took out enemy troops. Somehow, the supposed slowness of democracy yielded 22 million intricate gadgets, while dictatorial order failed to steadily produce even simple shells. The German ground forces meeting these fuses in December 1944 ranked among the globe's elite warriors. They had overrun much of Europe, battled on various theaters, endured prolonged fighting. They met their end in their dugouts, not from cowardice, but from clashing with what was coming next. They had those 30 feet, the span from the overhead explosion to the strike below, to see that their ideas about American frailty were dead wrong. In that split-second span, as shards flew from the triggered circuits to pierce bodies, the illusions of the Third Reich collided with U.S. truth. The proximity fuse ended more than just Nazi lives. It shattered the myth of tactical mastery, the allure of static defenses, the notion that bravery alone could best machinery. Across those 30 feet of sky, tracked by small radios with tech that defying belief existed, made in volumes thought impossible, America declared that tomorrow's battles would go to nations able to dream it up, build it right, and produce it in droves. Every German fighter felled by a proximity fuse overhead blast perished from a mirror. The essence of American industrial ethos took shape not through abstract doctrines, but via practical mechanics, not via rhetoric, but via manufacturing prowess, not via conjecture, but via the harsh realities of explosive impacts. Those munitions detonating 30 feet over German entrenchments hammered home freedom's rebuttal to tyranny in shards of shrapnel, demonstrating that open societies could surpass in output, surpass in ingenuity, and finally surpass in combat against despotic regimes. The proximity fuse stood as democracy's ideal instrument of war. Intricate, yet churned out in vast quantities, elaborate yet dependable, costly yet disposable. It dispatched foes with precision, driven not by malice, but by superior design. It resolved conflicts not via savagery, but via calculated precision. It secured triumphs not via brutality, but via manufacturing might. The tale of German foot soldiers confronting proximity fuses boils down to the clash of eras, yesterday versus tomorrow. Age-old shielding methods, honed across generations, turned irrelevant in moments. The ground that had shielded warriors from time immemorial now offered no refuge. The proximity fuse didn't merely eliminate German troops. It dismantled a whole paradigm of combat. Come December 1944, German infantrymen had just 30 feet until proximity fuse blasts tore their positions apart. Within that narrow span resided the divide between the era that had passed and the one emerging. They gauged their final resting places in meters. America gauged success in waves of frequency. Tomorrow had dawned. It came factory-forged and detonated precisely at 30 feet,